My lecture title is various kinds of the soft healings, the elastomer materials for three-dimensional printings. I am Professor Xiaoxuan Liu from Guangdong University of Technology from China. Okay, this is the graphics abstract. Here is a novel heat-proof polyurethane elastomer was developed to use the W networks structure systems. In the DN systems, the loosely close linkage the chemical networks was obtained was the photo-curable acrylics double bonds, acting as the robust molecular frameworks and maintaining the elasticity of the polymers. Simultaneously, the physical close linkage networks produced by the quadruple hydrogen bonds of the iridonucleotides usage can not only be achieved rapid reformations after fractures, but also the disappears then energies as a weak dynamic bonds. Ambulance the elastomer excellent self-healing ability and the highest stress ability. This is part one, the graph application. My lecture is the part two is slide highlights. I am Professor prepares the new silicone elastomer for the three-dimensional printings. He has many advantages, the self-reversibles and recycling the silicone elastomer realized by UV and thermocuring. And self-healing and recycling abilities derives reversibilities ions close linkings. A silicone elastomer was as apparent as the hydrolysis resistance. A silicone elastomer could be the three-dimensional printing into the hairs, the softened device. So this is part one, the content one, the self-healing the polyurethane materials. This paper is published on the Journal of the Molecular Chemistry Part C. Okay, so introductions. We can use the wood-borne polyurethanes and we prepare and by combines with the technology to prepare the self-healing polyurethane materials and to applications to three-dimensional printing materials. The wood-borne polyurethane materials have the many advantages. One is the tunable structures, two is the adjective properties, and simple is the synthesis process, and fourth is economics application rates. And we have used the healing technologies. The healing materials have the three advantages: the prolonged service lives and the more durable, the safer, and the lowering cost greatly. So self-healing polyurethane material applies a flexible spin sensors. We can use our sensors have the many advantages and outstanding price and tolerable mechanical stress and excellent adherence for metal, glass, and plastic, etc. A simple synthesis process productions to the larger scales productions, the wide selections of the conductive materials adjustable electron properties. So the flagship sensor systems many applies in many areas. So display the computation and the electrons and the human interface and health cares, etc. So we can research progress and material designs and the synthesis. This is the structure designs, the digital photo and the molecular weights of the WPU, and it is the segment the middles is the carboxyl aminos. So R is like this, or like this, esters. So it is UPR's names is DMPA and the DBLs as the catalyst. This is the waterborne polyurethane emergence or synthesis by the continuous isolate reactions where X and Y represented the more radius, UPIs and hammer. A synthesis process of the WPUs is illustrated as the follow the taking as the samples. This is the structure of the networks. So it is a physical cross-linking networks by the multiplies the hydrogen bonds, and this is the minimum. When the structurings, it is deformation largely. Deformation largely, it is loose the chemical networks, elastic frameworks. When the take out the stress and release to the orange structures. So this is the morphology of emerging particles and the structure, molecular structures. This is TEMs. So we can, the particle size, it is very small, and the distribution of the diagrams is very narrow. It's very narrow. It is a digital large skeletons. So it is FTIR spectrums. So we can, before UV curing and after UV curing, the amino carboxyls absorption band, it is clear changes. And the double bonds is the 1700 wavelengths. This is about 9% wavelengths. So figure D, it is NMR spectrums. So it is so the clear the multi hydrogen bonds and the polyester structure in structure. So the doors networks characteristics. This is conservations. So we figure 1, we clear C's. We have the different the conservation and with UH contains increased the conservation, it is increased up to the 90%, and the green lines. This is with NMR spectrums. This is different temperatures. When the temperature from the room temperature up to the 60 degrees centigrade, this is a bench, it is changes. So it is changes of the hydrogen bonds at the WPU's Qs and the different temperatures. A mechanical and dynamic mechanicals of the WPU's Q film. This is a tensile surface and with different U pies. The stress, it is have changes clearly to strength. To strength and strength, it is very long. Very long strength be about 600. And this is the cubes of the storage modulus, and the slightly changes. So it is storage, it is different changes. This is the tangent delta protein and the activation energies of the hydrogen. So we can activation energies of the hydrogen increase directly, lightly. So it is hearing the characteristic characterizations of the WPU's Q film. The upstream pictures, it is the optical macroscopic images of the creased and cured film before. Upstream picture, it is before, upstream before after healings. So we can source the upstairs. This is damaged and is heating 80 degrees centigrade for 24 hours heating. So it is heating 100 degrees centigrade for 90 minutes. And 3, it is heating to 120 degrees centigrade for the 15 minutes. So, and higher temperature, the healing times is shortened. So, next to it is strength and stance. The tensile properties WPU currents after healings. Figure B is at different temperature for 24 hours. C at the 100 degree for different time. So it is your logical properties of the circular deformation experiment. So we can end different conditions at the 80 degrees centigrade, G equals 1% or 50%. B is 100 degree, G equals to 1% or 100%, energy disappears. C is the stress strength cubes for the steps sucklings, the strength 100 to the 500%. So D, it is stress sucking sorting fixed at 100% strain after different waiting times. So it is so you and the clear pictures. schematic illustrations of fabrication and WPUs and the composition conductors. We have used the alkynes black such as ACTA. ACTA disappears into the suspension. Suspension and fabrication. We use session fabrication, the process of the feasible WPUs and assess composite conductors. Assess dispersion containing a little amount of the emergent smooth aspects as first level when the water evaporation, when the second levels of the WPU erosion smooth when the drops casting on the surface of the asset level. Like these pictures, a sector dispersion, the suspension and the spreading coating on the release substrate, and a sector performs the conductive layers, and we drops the coating, the WPU emergence when the evaporation of the waters. So it is put down nanoparticle selectors. After that, we can use the UV light exposure on the surface and surface for UV curing. UV curing and after curing and the release of the film. Release of film to forms the curable polymer and accession conductive lectures. So we can catch release on the release out the substrate. So it is the photographs the composition conductive. The conductive and the WPU's conversions and the CEM emissions. Figure A is the initial surface morphologies, and B is the being cut off to form the creek and very clear. And C is after healing for 5 minutes. Only 5 minutes. D is after 1 hour at the 100 degrees centigrade. So it is the healing effective is good. Rehealing behaviors. We use the dirt R to R sub-zeros, the radius at the 100 degree for different times, and up to the release the cuttings and the heating on the same locations. This is the radius and the rupture changes. This is 5 times on the same location, the cutting and healing against. And next, figure G to J. Optical emergence. G, it is conductor with LED light. It is very light. When the electrons put on the light, it is bright. And H is the cut of the 2 walls and breaking the circuits, and the R is disappear. And G is the LED was against after healing of the heating and light against. So variable fluxes senses settled from the WPU's assets. This is fabricate flexible stain sensors for the human motions detections. A is the dirt R to R sub-zeros was times for finger bend 0 degree stress and the 90 degree downwards. This picture is 0-degree stress. This is 90-degree downwards. So it is figure B, and the ample zero stress, and this is 90-degree upwards. So it is amber bending the terms from the 0 to 16th. This is from 0 to 16th. So it is the electrons, it is some the same. So it is shows the flexible synthesis. It is very successful. So conclusions. The double networks designs principles to synthesize environmental friendly heatable UV curing the waterborne polyurethanes. And POW allows the cross-linked networks as a potential was curing of the double physical cross-link, the high stress and the good silence with a fragrance, several healings, the performance. And composition conductor possesses both excellent, inherent, and unique materials behaviors. The proofs of the conceptions experiment suggest that the composite conductor can be employed and flexible sensors on the human skins by the successful detector, the by signal of the finger and elbow bendings. So that is part 2, and here's the silicone elastomers. Elastomer, the paper, it is published in the chemical engineering journals. So it is research works significant. It is very important. So we can use the UV curing technology and combination to apply it to the silicon materials and to aggregations photo-curable silicon materials have many advantages: the simple reaction conditions, the structure and conservable, and the rapid curing, the energy convergence, and the environmental productions. And we have the and the traditional and the silicon materials have some shortcomings and oxidations and poor mechanical properties and soil curing rate and compactility pores. So we can change this shortcoming. We aggregations the self-healable UV curing silicon materials and self-healable materials have the many advantages: long-term usages, reliability, durability, costing conductors. So it is self-healing materials. The prepares methods is 2 means methods. It is interest and the interest. We are used in interest, and reviewing and 3-dimensional printings for silicon elastomer have not yet entails with simple healing abilities. So means contents, the research programs, the window terminated the polar esters, the properties, and the Swiss modifies the silicones oils, and carboxyl modifies silicon oils, amino modifies silicon manners, and use the photo initiator. We have the 1, 2, 3, 4 new monomers. So we can use the photo and small dark curing and the mechanism properties and the physical properties, kinetic reversibles, the self-healing abilities, responsible abilities, transparent, and the hydrolysis resistant and the 3-dimensional printings. So we can use use the curing silicon materials, and the silicon materials characterized by the many modern technologies such as FTIR, DSC, NMR, XRD, etc. So we can the schematic illustration of the photo and small dark curing and cross-linking networks of the silicon elastomer. Elastomer, it is it is a 3-dimensional modification. It is the red lines, present red lines. It is double bonds dimensions modifies black lines. This is carboxyls and the green branch lines and the red branch lines and the mono. And to the and UV curings and TPO, it is the photo initiators who can, after UV curing, and to form the structures and to carboxyl and the amino together this. And after that, we can hold heating. We can heating to different temperatures, and the silicon and the some hydrogen bonds to form the cross-linking networks. So it is can photo small during curing the mechanisms. This is on the UV light on and beginning exposure. Exposure beginning and in situ rheological testings. After the UV exposure on, the relations of the system, it is very different. So it's very different, it is increased. So it is real-time FTIR spectrums, the double bonds or the 0 to 7 quick reactions conversion, it is up to the 90%. Very, very high conversions. So as physical properties of the thermal and the thermal photo and thermal cross-linking silicon elastomer. This is the FTIR spectrums, and before it is UV irradiation, and after irradiation, but before heated. After the heated, the 3 different RF cubes. The special absorbance have the responding changes. like this. Like this is 3069 is 2575 and 1615. And WX are these different, and the crystal reflections funds, it is have the regular changes. So it is the thin strength, it is persistent is the highest stressing strength, maybe and from the 270 to 360. So dynamic reversibles of the photos cross-linking the silicone elastomer. So it is use the vibration temperatures infrared spectrums. The peak softens heat to from the 40 degrees centigrade to 120 degrees centigrade by the heating rate is 10 degrees centigrade per minute. So we can, the carboxyl absorption bands, it is changes, and the softer, it is softer to the reach. So it is a left figure, it is temperature is increased from 20 degrees centigrade to 120 degrees centigrade from the 40 degrees centigrade. This is heating. As it's cooling down from the 120 degrees centigrade, the cooling down to 40 degrees centigrade. So it is the reversible as the peak shifters. Dynamics reversibles photo cross-linking silicones. This is storage modulus changes the Qs, and this is different the samples. One is the ion samples, ions networks, and the TE and ion chain. Ion networks used contains is 10% samples. This as the different the stress different modulus. And dynamic reversibles photo silicon photo and small cross-linking the silicon elastomer. This is the normalized stress relaxation surface, and the TE and AN10 samples and different temperature. It is figure A. B is elastomer containing various ion bonds at 60 degrees centigrade. C is the end fitting of the relaxation time. The time towards temperature according to the Arrhenius equations. D is stress relaxation action energies of the sample with various ion bonds. So which is this pictures and the regular changes in every picture or every curves. So and relaxation activation energy, it is different decreased. So it is the stress relaxation. So we compare the abilities to the this is arranged to form the structure close-linking the structure, and the cut off the two parts. It is cut off and here, and to reforms the one structures. So it is 2 cuts 1 time and hearings, and 2 times and hearings, and 3 times and hearings. They repeat the macros repairings of the damaged TE and N10 samples. So it is mechanical properties. It is persistent factors repeatedly hit the TE and tempo. It is persistent highest the stress. When it is the strength, it is no changes. So we worsen is black, and 1 time, 2 time, and 3 time. So this is the difference of the sample hearings at the 100 degree for the 20 hours. So it is like this. Responsibilities, and so we can stress strains cubes the worsen and reprocessing silicones elastomers. B is photo grams of the reprocessing of the TGIs. So it is the simple pictures. So it is a create smart to the pattern material and the small and heating and pressing. Small and pressing to reforms the film so soft, and to prepare the sampling to requires and damage and cut down to parts and self-heating together. Heating together is and filter bees repeatedly and reprocess and 10 sample from the 80 methyls. 80 methyls is bees. Sample properties, sample healing properties replaces the TEIN10 samples. Next, let's show you transparency and hydrolysis. Transparency, we have the silicone elastomer have the very highest visible light transparent. So it is transparent is up to the 90%. After heating times, it is slightly directly, but its persistence 88 above. 88 above, and the highest transparency is Y high up to the 60%. So it is thin strings have the good persistent factors. This is tenuous. So we can use the 3-dimensional printings based as SLA technologies. SLA, we printing the GDUT, Guangdong University Technology. This is my names of the technology. This is the star samples and the rainbow star samples. So it is stressed. It is things. It is highest to the 400 to the 450s. So it is cut down 2 parts, and here's to it is reforms one the good rainbow stars. So a conclusion: a sample siblings recycling silicon elastomer realized by UV smoke curings. the self-healing and recycling acids derivative from reversible ionic crosslinkings. And silicone elastomer was transparent as hydrolysis resistance, and the silicone elastomer would be the 3D dimension printed into the sample hearables softened device. So it is a different 1, 2, 3, 4, 5. It is the recent my team's publications in the Progress in Polymer Science, Progress in Organic Coating, and the Journal Material, Chemical Passy, and the Chemical Energy Journal, and the ACTA Polymerica Sinicas, and this is cover paper. So it is which the recent I research, my team's research works. So the works have been finished by my PhD student and my younger teachers in my groups. I thank all of their contributions. I thank the National and Natural Science and Funding of China and etc. Progress and Funding. This picture is PhD Yang Yan. This PhD Liu Zhu. This is post-PhD Zhou Jinyi. This is a younger professor, Xiang Hongping. Yes, thank you all. So this picture is just photos at the September 10th. The days is a celebration of the Teachers' Days in Guangdong and 220 in China. Thank you, your attention.